Okay, so Ohm's law. Interesting in here is resistors. So remember, or maybe you don't remember, but when we looked before at our circuit, so I had a circuit, didn't I? I've had these circuits a few times. So you draw a circuit in your books and label it where we've got to so far. Best not to draw it in pen because it's going to be hard for you to make adjustments to it as you go along. Just draw it in pencil. You might notice that my wire here, straight lines, this is the convention for our circuit diagram, to draw our wires like that. That's quite done with my red. Okay, so what is this? Battery?
Is it a cell or a battery?
It's like a battery cell.
Why is it a battery and not a cell?
A battery is made up of multiple cells.
Yeah, a battery is made up of multiple cells. So this is one cell. And any number would then be a battery. Just like if you have one hen in a cage, that is one hen in a cage. If you have a row of hens in cages, they are called battery hens. It's the same thing. Right, now, what are the charges on my battery?
Negative.
What's this charge?
Positive.
Okay, now I want to label my current. Which direction does my current go in?
Anti-clockwise.
That way.
Toward the negative.
Towards the negative. Okay.
Yeah. So clockwise.
Anti-clockwise.
Oh, what's it?
Because clocks go the other way.
And current is the same positive, remember?
Right, so yeah, by definition, current is a motion of positive charge, and so it would be moving away from the positive terminal and towards the negative terminal. But we know, in fact, that it's the electrons that move, and so what's the direction?
Clockwise.
They're going to move clockwise.
That's what I was thinking of.
Yeah. So we can think about the battery is what's giving the electrons the push. It pushes the electrons. So the more powerful the battery, the bigger the push. And here the wire is offering very low resistance to the pathway of those electrons. And so they can move quite easily through the wire. At the moment, what's this? I haven't labelled this.
A switch.
A switch. And this, at the moment, what I've drawn is a short circuit because we haven't put in a resistor. We haven't got this circuit doing any work. And what would happen is that the wire gets really hot. And if we left it on and we had it was big enough battery, it might start a fire.
Is the circuit broken at the moment though? Because the switch
Oh yeah, if the switch was closed, yes. So I'm going to close my switch, but I'm going to put in
Resistor.
a resistor. And this is where the work is going to be done in my circuit. And the resistor, if it has high resistance, means to the flow of electrons. And so it's going to make it harder for the electrons to flow. But it doesn't just make it harder for the electrons to flow in the resistor. The flow of the electrons is constant in the circuit, and so this is going to dictate how fast all of the electrons move. So electron flow notice too, because there is only one path. In this simple circuit, they can only go round and round like this. Yeah? And depending on how much the resistor, what the resistor is, this is going to determine the flow rate for all of the electrons it's in my pocket in this circuit. So we have a relationship called Ohm's law, where V equals IR. So now we have the resistor, and resistance is measured in ohms. And its symbol is omega. And volts, we're already familiar with volts and V. And this is my current, which is in amps. Does that sort of make sense? And this relationship should be on your formula sheet, so I'm pretty sure it's because V equals IR. Wonderful. And you can think of the resistor as being also constriction in the pipe. So if instead of having electrons flowing, we have water flowing, representing the flow of electrons, then this is the constriction in the pipe.
So it's like a bottleneck.
A bottleneck. And so nothing can go faster than the bottleneck. Okay? They're all sort of going to go around at the same pace. Okay? So in our resistors, and of course, we couldn't go past this part of the course without a reference to the Borg, who are my favourite bad guys in Star Trek, who say resistance is futile. We are the Borg. Resistance is futile.
Does anyone watch Star Trek?
Possibly.
I think it's just you, so.
I'll tell you what, you're missing out.
Isn't it like really old?
Have you?
Real, watch yourself.
What did you say, Brett?
She said, isn't it like really old? It's Star Trek. Just kidding.
Like that is easy.
Have you marked out tests? Oh, I don't know. No, that's not fast.
You've got a test on Thursday.
Yeah, okay. So your marks looking pretty good, Bria. Not.
Okay, so we can talk about resistors as being ohmic or non-ohmic. Ohmic means that they have this straight line relationship between voltage and current. And the gradient then is equal to the resistance of the resistor. Okay, so it's called an ohmic resistor resistor because its resistance is constant over varying voltages or currents. But we also need to consider what we call a non-ohmic and this is one where the resistance is going to change. And an example might be an incandescent light bulb, where its resistance will change with increase in voltage will go an increase in temperature. And so when it's cool, it has less resistance and when it's hot.
Questions. Is it I over V or V over I for the graph?
Well, if we're thinking, what would it look like here if I changed them around? It's going to be the same, isn't it? But V equals what? IR. So,
Which
yeah.
really great is rise over run.
So it would be
So
V.
then like it should be all the way down.
V on the y-axis and I on the x-axis.
You should have,
It should be V over I, rise over run.
it should, yeah, we can do it. Yeah, sure.
Doesn't matter which way it goes.
No. Well, in the context of these questions, I was just copying basically what's in the booklet because it doesn't really matter in one sense that because if you've got a linear relationship with the I on the Y, you're going to have a linear relationship with the V on the Y as well. Yep. And so that's the way it's normally represented.
So our equation isn't valid for a non-ohmic resistor.
That's right. Which means that you can't use this equation. For a non-ohmic resistor. Now, just say you get a question in a test or an exam that you look at it as an incandescent bulb and they're asking you to calculate something like voltage, for example. The correct way of answering that will be to do the calculation, not to write and say I can't use this relationship because it's an non-ohmic resistor. Okay, if it's asking you to calculate. Don't analyze the question. Yeah, our resistance here, resistance will equal V over I.
Once it gets to like a light bulb, when you turn it on, it's not very bright. And then once it gets to a certain temperature, wouldn't it stay at that max temperature for the whatever it's called? So then that would become then linear.
Yeah, well look, depending on what kind of resistor, it's not even going to be this shape either. Okay, this is just a generic shape, but and a lot of this isn't quite right. So you just learn the content for the course, the way it is, and then if you go on to study physics further, then you'll see where things change really. our template, if you like, for an ohmic resistor and a non-ohmic resistor. And look, I totally get what you're saying, that if we were calculating, we should have them around the other way. But just note that if you have them like it's written in the book here, it's still going to be a straight line. And this, if we had it the other way, like I've changed the axes around, we could end up with something like that too. So the point is, this is non-linear. So that as we either change the voltage or change the current, and that's normally why the voltage would be on the x-axis, because we're changing the voltage. Like that's the and then you measure the current. So that's the variable. Does that make sense? Sort of? Someone say no? Did you say no?
Trying to get to X.
Yeah, but would you like me to say no?
I'm still remembering about what you said about Star Trek.
She's holding a bit of a grudge there, Bria.
What other shows do you like?
Oh no. Subject.
Star Trek. The other way.
What about
The Brady Bunch. You not watched that back in the day though? We watched
I'll
it.
tell you what, you're digging a hole for
Is
yourself.
he trying to?
No, that was a good show.
What about Star Wars?
Star Wars.
Star Wars.
Full House.
Some of Star Wars.
What, like the
I
prequels?
love that.
Absolutely not. I hate the prequels.
The prequels are the best ones.
Okay, there goes Jackson's mouth.
What about Marvel? Do you like any of the Marvel movies?
I'm not a big Marvel fan.
Full House.
Full House.
Never watched it.
Sue.
Okay.
Maybe she
Your
is
marks
too
are going
young.
down.
Maybe she
Home
is
and
too
Away.
young.
Oh, what? Never watched Home and Away.
Oh, I don't. It's bad. Never do.
Maths.
You gotta catch up in one episode, so.
Here we go. Worked example. It's on page 37. A typical compact fluorescent light bulb draws a current of 0.10 amps. So 0.10 amps is the current. What is its resistance when working normally? What we need to know is that if we plug it into a power point in Australia, the voltage will be 240 volts. Approximately.
So if it doesn't state like what the voltage is, just go to like before.
Yeah, but it told us that like it's a light bulb, and it didn't tell us, so we have to assume we've plugged it in here. Yeah. We want to know its resistance. So V is IR, and we've already determined then that R is equal to V upon I. So 240 divided by 0.1 gives us 2,400 ohms. Now we've got another circuit. What would each of the meters read in the circuit in the diagram below? So we have our circuit. You see that we've got this kind of arrangement. What does that mean? The resistor, and it tells us it's a 4 ohm resistor. Oh, the batteries are around the other way in the diagram, 12 volts. And we're asked, what would each of the meters read? I'll put in my voltmeter. And we've got 2 ammeters. What do the ammeters measure?
They measure the current.
They measure the current. And what do we know about the current in this circuit?
That it's the volts divided by the resistance.
Okay, so if V equals IR, I equals V divided by R. Gives me 3 amps. what we know for this circuit is that that's the current anywhere we measured it. It wouldn't matter where we put these ammeters. We could put them here, or here, or here, or here. They're all going to measure 3 amps. Because remember, the resistor is dictating the rate flow of the electrons in the circuit, and so it doesn't matter at which point we measure, it's going to be the same. That's why we can measure that for the whole circuit. What would we measure? What would the voltmeter measure? It's going to measure the volts, and what are the volts going to be? 12 volts, yes? Because we've only got one resistor in this circuit, it's being used in this resistor. So this meter, sorry. It's going to be 12 volts. Now, the work example is 6.5.3, which is so many bits.
I'm joking. Just unplug functions at 10.
What is the resistance of a car headlight if there is a current of 5 amps in it when operating normally? So here we've got a code 5 amps, and this time we have a 12 volt battery. We should all know that that's the 12 volts in the car. And we want to know the resistance. So VIR is V on I. R will equal 12 divided by 5, which gives me 2.4 ohms. Any questions, queries, comments?